What is the difference between classical physics and general relativity? What does quantum mechanics deal with? What is the difference between kinematics and dynamics? What is the meaning of instantaneous acceleration? And what is the difference between speed and velocity? If you answer to all or most of these questions at the end of this lesson, then it means you understood the topic and can proceed to the next lesson. Here, we begin studying the different branches of general physics separately and in detail. This presentation is dedicated to the study of mechanics, with an emphasis on the kinematics section. Motion can be described using the two disciplines of kinematics and dynamics. The difference between them is that kinematics describes the motion using properties such as position, time, velocity, and acceleration, while dynamics describes the cause of motion using Newton's laws of motion. Based on the style of study, physics is commonly classified into three main subfields: classical physics, quantum physics, and general relativity. In this context, classical physics mainly refers to Newtonian mechanics, that is, physics that does not involve quantum mechanics or the theory of relativity. Classical physics typically applies to macroscopic systems, from everyday objects to planetary motion. It can also be applied to microscopic systems, such as molecules and atoms. However, it becomes less accurate at atomic scales, where quantum effects dominate. Moreover, in classical physics, objects move at velocities much smaller than the speed of light. General relativity applies to very massive objects and cosmological scales, where gravitational effects are strong, or where objects move at velocities close to the speed of light. In fact, Newtonian mechanics can be regarded as a limiting case of general relativity under low velocities. Quantum physics applies to very small scales, typical on the order of 10 to the power of minus 10 meter or smaller, such as for atoms, electrons, nuclei, and elementary particles, where quantum effects become important. Before diving into kinematics, it's essential to define some key concepts. In physics, quantities are classified as either scalars or vectors. A physical quantity that can be specified only with numbers is called a scalar. In other words, scalar is a synonym of number. Examples of scalar quantities are time, mass, distance, length, volume, temperature, and energy. Many physical quantities, however, cannot be described completely by just a single number of physical units. Physical quantities specified by both magnitude and a direction are called vectors. Examples of vector quantities include displacement, velocity, position, force, momentum, and torque. We will focus on some basic vector analysis when we study projectile motion. It will be clear how to work with vectors in 2-3 dimensions. Let's also introduce some other important concepts. In mechanics, all objects are considered as material points. A material point is an object that has mass, but whose dimensions, size, shape, and structure can be neglected. This will not be explicitly mentioned later, but will always be implied. Another important concept is the frame of reference, which refers to an arbitrary set of axes used to describe the position and motion of an object. Based on the number of dimensions, motions in kinematics can be classified into several types: linear or one-dimensional motion, two-dimensional motion, and three-dimensional motion. In this lesson, we will focus on linear motion, which is further classified into horizontal and vertical motions. A comprehensive study of kinematics involves analyzing motion in 2 and 3 dimensions. For now, we'll examine motion in 1 dimension, as it provides the foundational tools needed to study multidimensional motion. A good example of an object undergoing one-dimensional motion is a motion of car, train, or bus. When you are in motion, the basic questions to ask are: where are you? Where are you going? How fast are you getting there? To answer this, you need to specify your position, displacement, and average velocity. All of these quantities can be described using kinematics, without needing to know the train's mass or the forces acting on the moving object. The change in position is called displacement. The term displacement implies that an object has moved or has been displaced. Position is a numerical value of x along a straight line where the object is located. Displacement, on the other hand, refers to the change in position along this line. Since displacement includes direction, it's a vector quantity and can be either positive or negative, depending on the chosen reference direction. The Greek letter delta represents change in whatever quantity follows it. For example, delta x denotes the change in position. To calculate displacement, the initial position is subtracted from the final position. Note that the System International, or shortly SI unit for displacement, is a meter, although other units, like kilometers, are sometimes used. If units other than meters are given, they may need to be converted to meters to complete the calculation. To calculate other kinematic quantities, the time variable needs to be introduced. The time allows us to describe not only where the object is during its motion, its position, but also how fast it's moving. The rate at which an object's position changes with time describes its velocity. If we are not concerned with the details of the motion at each instant, we typically express this rate as average velocity. This vector quantity is simply the total displacement divided by the elapsed time, the time taken to travel between 2 points. These quantities can be better visualized on a graph. Here the graph is a straight line, meaning there is no acceleration, and the object moves with constant velocity. The equation that describes this motion is known as the equation of motion. We have now seen how to calculate the average velocity between 2 positions. However, since objects in the real world move continuously through space and time, we are interested in finding the velocity of an object at any specific point in time. To do this, fundamental principles from calculus are used. The quantity that tells us how fast an object is moving at any instant along its path is called instantaneous velocity, often referred to simply as velocity. Mathematically, instantaneous velocity is the limit of the average velocity as the elapsed time approaches zero, or equivalently, it's the derivative of position with respect to time. In everyday language, people often use the terms speed and velocity interchangeably. However, in physics, they are distinct concepts. One key difference is that speed has no direction. It's a scalar quantity. To calculate average speed, we find the total distance traveled divided by the elapsed time. Understanding acceleration is crucial not only in our daily lives, but also in fields ranging from space acceleration to subatomic physics. In everyday conversation, accelerating usually refers to speeding up. Acceleration refers to the rate of change of velocity over time. It's a vector quantity, pointing in the direction of the change in velocity. Importantly, acceleration is not always in the direction of motion. When an object slows down, its acceleration is opposite to the direction of motion. This is commonly called deceleration. Instantaneous acceleration, the acceleration at a specific instant in time, is calculated using the same approach as instantaneous velocity. It's a derivative of the velocity function with respect to time. In general, the equation of motion with constant acceleration is given by equation 1. The plus-minus signs in front of the acceleration term depend on whether the object is accelerating or decelerating. This equation is fundamental for describing the motion of an object. To find the velocity as a function of time, equation 2 is used. If time is unknown, the velocity as a function of position is found by equation 3. Let us consider the following graphical illustration, where the object is moving according to the following equation. The position time graph is upward opening parabola, indicating the motion under constant acceleration. The motion consists of 3 stages: motion in the negative direction with decreasing speed, a brief stop, and motion in the positive direction with increasing speed, all under uniform acceleration. Keep in mind that the particle does not move in a curved path in a space as shown by the blue curve in the graphical representation. The particle moves along the x-axis in one dimension. Here is an example exercise related to the topic. Solving this task will help you better understand the concepts and apply the formulas introduced earlier. It's recommended that you attempt the task yourself to reinforce your understanding, save time now, and continue progressing with the basic theory. It's well known that in the absence of air resistance, all objects dropped near the Earth's surface fall towards the Earth with the same constant acceleration due to gravity. However, this conclusion was not widely accepted until around 16th century. Galileo Galilei was the first to introduce our modern understanding of falling objects. For example, if two objects with different masses are dropped simultaneously from the same height, neglecting air resistance, both will experience the same motion and hit the ground at the same time. This idealized motion, in which air resistance is absent, is referred to as free fall motion. A freely falling object is any object moving under the influence of gravity alone, regardless of its initial motion. Objects thrown upward, dropped from rest, or even thrown downward are all considered to be freely falling once they are released. In all cases, the object experiences an acceleration directed downward, regardless of the direction in which it was initially moving. The free fall acceleration is denoted by the symbol g. Its value near the Earth's surface decreases with increasing altitude and slightly varies with changes in latitude. At Earth's surface, the value of g is approximately 9.8 meter over second square. Unless specified otherwise, this value will be used in calculations. For quick estimates, g is equal to 10. If air resistance is neglected and the variation of free fall acceleration with altitude is ignored over short vertical distances, the motion of a freely falling object can be treated as motion under constant acceleration in one dimension. Therefore, the equations of motion for objects moving with constant acceleration in the horizontal direction can also be applied to vertical falling objects. The only modifications needed are to recognize that the motion is in the vertical direction rather than the horizontal, and that the acceleration is downward, with a magnitude of 9.8 meter over second square. Here is an example exercise related to free fall motion. The solution process for this task is left for you to complete on your own. Let us now turn to the final topic of this lesson. Before, acceleration is found from velocity, and velocity from position. Now, by applying integral calculus, this process can be reversed. Velocity can be found from the acceleration function and position from the velocity function. The corresponding formulas are given in equations 5 and 6, where C1 and C2 are the constant of integration. Once again, an example exercise related to the topic of inverse functions is provided here to help reinforce your understanding. We have now reached the end of this lesson. Do you remember the summarizing questions in the beginning? If you answered to all or most of them, then you did a great job understanding the topic. Otherwise, it's recommended to watch this presentation carefully again. In the next lesson, we will study two-dimensional motion, which involves topics such as projectile motion, relative motion, and angular motion.